It's a pleasure for me to introduce the next speaker, Professor Dima Shlyakhtenko from UCLA, and the title of his talk is Cohomology and L to Betti numbers for subfactors and quasi-regular inclusions.
Right, well, thank you very much. I'm very grateful for the organizers of this program for the possibility to speak here. So this paper that I'm talking about is joint work with Sorin, Popa, and andStefaan, Vaes. And well, the purpose of this was to try to understand what is a good cohomology theory or homology theory for subfactors. Now, the origin of this paper was quite funny in that somehow we all had, for actually probably initiated by Sorin, we all were kind of searching for answers as to what this theory should be. And we had various ways of approaching it from different angles, and the kind of miracle that happened was that actually in the end we found that all the definitions are the same, which was actually very comforting to us because you know, of course, subfactors is such a big field, and then you don't want to create a monstrosity that sort of is not working very well. And if you want a kind of a short takeaway, if you want to put this talk on Twitter and kind of do a hashtag something, the hashtag should be Morita equivalence. So hashtag Morita is the carry out of the whole thing. Okay, so what is cohomology of whatever? Well, it's very easy actually. I mean, you start with whatever object you want to take a cohomology of, then you have to take some coefficients, and then you write a big H, and then to indicate it's a cohomology you put a K up above. That's basically what it is. The devil is in the details, as they say. Well, let's take one very classical situation, which is the Hochschild cohomology. In this case, A would be just an associative algebra. V would be an AA bimodule. So that's a vector space that carries two commuting actions of A, one on the left and one on the right. And then one looks at CK, so these are maps from, and I always get the grading incorrect, from the kth tensor power of A into your coefficient bimodule V. And on this space of maps, there is a Hochschild differential, which is D. So if I have such a map, let's call it, I don't know, phi. So D phi. So that will be an element in Ck plus 1, so it will have k plus 1 arguments, and so if I evaluate it on A0 tensor n, then, well, the first and last terms are kind of special. The first term is that I take A0 and then I evaluate phi on A1, An, and then I act with A0 on the left. The next term will be where I multiply some of the terms together. And then I multiply the next two terms together, and so on. And then, well, the last term will be something like this. The next to last term, I should say. And then there's one more term, which is where I use the last an to multiply things on the right. Okay, so here I'm using the bimodule structure twice, here and here for the left and right action, and then in between I'm using the algebra structure to multiply things together. And then, of course, what one does is one calls, what is it called, ZK, I guess, the kernel of D inside CK, so the space of closed. These are called cocycles. This is the space of closed cocycles. And BK, the co-boundaries, is the image of D. and then the cohomology is what is it, zk mod bk. Right? So this is a very classical object. There's one variation on it, which I should mention right away. Sometimes one variation. If you start with what's called an augmented algebra, so that means that you have a map from A into C. And a good example to keep in mind is the algebra of a group, in which case the augmentation is something that takes a sum of group elements into simply the sum of their coefficients. So each group element is taken to 1. Then very often one assumes then often takes as coefficient say right A modules, which one makes into a bimodule by taking the trivial action on the left. So viewed as A bimodules using as left action. And if you do that, then you will descend back into what is called group cohomology, which is the specific case where you take the algebra to be that. Now, just for my sanity to check that things work, I mean, kind of the first interesting case is k equals 1. So in this case, we're interested in maps phi from A into V. And then the cocycle condition, so the condition that d phi is equal to 0, if you write it out, translates into saying that if I look at d phi of A tensor B is equal to A, so that should be 0, right? And that's A phi of B minus phi of AB plus B, what am I saying? Phi of AB, right? And then, in other words, what you have is the familiar Leibniz property, which is A phi of B minus phi of AB. So the one cocycles are precisely derivations. So C1 is the derivations from A into the bimodule V. And here on this side of the board, if you now fix gamma in a representation of V of gamma, then if you chase through what that means, C1, these are the cocycles, one cocycles, so these are maps C from gamma into V with the properties that C of GH is equal to C of H plus C of GH, where this is the action of the group on V. Right, so there's one here. This is an invisible epsilon of G, if you like, that goes in there. Okay. So this cohomology theory was introduced by Hochschild, and from what I understand, it was very much motivated by the following fact, that if you take gamma, the fundamental group of some x, and x tilde is contractible, then actually, if you're interested in the this cohomology of C gamma with coefficients in the trivial module, all you get is cohomology. Sorry, all you get is the usual cohomology of X. So this is the usual simplicial. So from that you can get all kinds of facts about this cohomology. For example, if you take gamma to be Z, that tells you that of course, the x you will take here is the circle, right? The universal cover of that is the real line which is contractible. And so what you find is that the cohomology of z with coefficients in C is just the same thing as the cohomology of the circle. So let me write it S1 to indicate that this is a topological space, not a group, with coefficients in C. And this is, of course, just Z if, sorry, C if k is equal to 0 or 1 and 0 otherwise. And another thing that you can easily check is that hk of a finite group with coefficients in C is 0, well, at least for k, I guess for all k, well, k at least 1, I guess, to be safe, which simply has to do with the fact that, I mean, of course, this has non-trivial cohomology if you put some torsion in there, but generally speaking, there is no interesting cohomology to be had. Remarkably, there's another interesting and canonical choice of coefficients here. Of course, C is one natural choice of a module over a group, but there's another canonical choice of coefficients, and this goes into the subject of what's called L2 cohomology. Namely, one looks at the cohomology of a group with coefficients L2 of the group. Okay. Here things get a little bit subtle, and if you really want to avoid some of the subtleties and just stay algebraic, the correct coefficients really here are affiliated operators to the von Neumann algebra of the group, which is some kind of completion of L2. Okay, but let's just ignore that a little bit. And what's nice about that is that if you chase through how this thing is going to be defined and so on, you will see that we will be using up the fact that L2 of gamma is a right module over the group in defining cohomology, but it will be left for us the fact that still the group acts on the left on this module. So in fact, this cohomology group will still inherit a left action of the group, which in fact will be an action of the group for Neumann algebra. So these are modules over the group for Neumann algebra, and so you have these things called the Atiyah Chigo-Grom of L2 Betti numbers, which are the dimensions over L of gamma of hk of gamma L2 of gamma. And I mean, just to again be very, very basic, if I look at the situation where k is equal to 1, then I'm simply looking at cocycles, so maps from gamma into L2 of gamma, which satisfy this property. Well, let me write it this right regular representation of h times c of g. That's what I'm just copying from this cocycle condition there. And then you can, if your group actually is finitely generated by some elements g1, gn, then you can encode such a cocycle by recording its values on the generators, because this is a kind of a Leibniz rule that allows you to compute the cocycle on arbitrary words in the generators in terms of shorter words, and so therefore it's completely determined by that. And so in fact, this what I call there Z1 embeds naturally into L2 of the group direct sum n. And then you have the inner cocycles. These are cocycles of the form C of G equals to xc minus rho of G xc for some xc in L2. These are the inner ones, and then if you mod out by the inner, then the cohomology is Z1 modulo of the inner. Okay, and so this theory of L2 Betti numbers is actually, I mean, it's quite a significant portion of geometric group theory. And I mean, just for fun, let me tell you some things about it. I mean, for instance, it turns out that all the L2 Betti numbers of gamma are 0 if gamma is amenable. Let me just say that k is at least 1. I mean, if you wonder about the 0th Betti number, turns out to be this is 1 over the order of the group, with the idea that if the group is infinite, that's 0. And then you have various things which are kind of inspired by algebraic topology. For instance, if you look at the kth L2 Betti number of a free product of two groups, and then what you get is essentially the sum of these L2 Betti numbers. So that's if k is at least 2. But then the first Betti number is sort of funny. It is the sum of the two. But then it's plus 1 minus beta 0 of the first one, minus beta 0 of the second one. And if you want to know why there's this funny thing, it's because somehow when you model the space in which the group acts and so forth, you have to take some kind of a join over a point. And so things are kind of special in dimension 0 because of some various formulas. There's a Kuhneth formula if I want the Betti number of a product of two things, and this is the sum of say a plus b adding up to k, the 8th Betti number of the first group times the bth Betti number of the second group. Okay, so there are many interesting things that allow you to compute these things. And all right. Now, so what we wanted to do when we started working on this was to try to upgrade this situation to deal with subfactors. Now I say upgrade because we know, of course, that subfactors have a kind of a group-like symmetry. There's a group-like nature to them in some way. Namely, if you start with a group G, group gamma, which is generated by some elements G1, Gn, it is always possible to produce a subfactor that encodes this group by looking at the following thing. You fix an action of gamma on some for Neumann algebra M, and then you look at the following embedding. You look at M being embedded into n by n matrices, well, I guess n plus 1 matrices over M, by sending say x to the matrix X, and then I take G1 acting on X, Gn acting on X. And so this has the feature that if you look at the subfactor, provided that this group, this action is chosen correctly, that it's appropriately outer and all that, that if you look at the associated representation theory of this representation category, the C star tensor category associated to the subfactor, then that is just the group. So it's just the group ring. Okay. So there were kind of two ways to proceed here, and one way is what we found later somehow. You see, there are kind of two ways to encode this group-like symmetry of a factor. One way is the C star tensor category. And the second way is what is called, so if you're given a concrete subfactor n into m, what is called the quantum double. So the inclusion of M tensor and its opposite into a special special algebra, which is Sorin's symmetric enveloping algebras. So somehow these are two distinct ways of encoding this kind of symmetry. So in what way are they distinct? So I told you that if you start with a subfactor that is just created from a group, the C star tensor category will be just the group. So the irreducible objects will be the group, the elements of the group, and then the tensor products of these things will simply be the product of the group. Here, however, so for the subfactor inclusion there that comes from the group, this will be of the form M tensor M op into M tensor M op cross product gamma. So it will be a cross product type inclusion. Okay. So so there are these kinds of two different ways of seeing the group appearing in this context. Now, so probably the more familiar language to this audience is the language of the C star tensor category. So let me say everything in that language, and then I will tell you the corresponding language in this inclusion. And for this inclusion, the key fact here is that this inclusion is what's called quasi-regular, which means it's kind of like this. Not exactly a cross product by a group, but by some kind of a group-like structure. All right, so let's start the definition. Suppose we're given a C star tensor category C, so we have the set of irreducibles on C, right? We have for say alpha and beta irreducibles, or in general elements of C, we have their tensor product, which I'll just denote by alpha times beta, and then I'll write alpha beta for the Hom space between alpha and beta. So this is the space of intertwiners between elements alpha and beta. So then the important object is what's called the tube algebra. So this is an upgrade of something that, well, somewhat in the spirit of what Okhnianu introduced a while ago, but it's an upgrade to an arbitrary tensor category. So what is this? Well, it's going to be, as a linear space, the direct sum parametrized by choices of 3 irreducibles. And then the direct summand corresponding to this triple is just going to be the set of all intertwiners between I alpha and alpha j. Okay, so this will be a certain finite dimensional piece. Now, the way you define the multiplication in this algebra is that if you take V and W, so V and W are going to be intertwiners. Let's call this. Let me call this algebra A, and let me call Aij to be the piece that corresponds to I and j here. So it's the direct sum over all alpha of I alpha j. So the ijth piece somehow. So the multiplication will be defined from Aij say j prime k to A I k, and it will be 0 if if j is not equal to j prime, and otherwise if I take an intertwiner V and an intertwiner W here, then the product of them will be simply V tensor 1 times 1 tensor W. And if you follow through what this means, you will see that sort of makes sense. Raise that whole thing up. Okay? So this algebra, I mean, sometimes it's called an algebroid because the multiplication is 0 half the time, but it really is just an algebra. It has some canonical central projections, pi. So these are the identity map between I epsilon and epsilon j, epsilon I, that lives inside aii. And if you look at the subalgebra B, which is generated by all these pi's, and that's a canonical abelian subalgebra of that whole thing. And so now it turns out that this algebra is very nice in many ways for the purpose of describing math around these categories. For example, the representation of C turns out to be, I mean, if you like, you can define it to be simply a representation of this tube algebra A. And that gives you a nice representation theory and previous, I mean, essentially the content of the previous work of andStefaan and Sorin can be summarized by saying this gives you a very nice notion of representation for subfactors, or for these kinds of categories in particular. Okay. Oh yeah, and I should say that also this algebra comes with an augmentation. Let me put it here. So the augmentation goes from A into C, and it's simply that it takes each one of these projections to 0 if I is not the trivial module. And then if you look at epsilon of the identity alpha, so here I'm regarding this as a morphism between epsilon alpha and alpha epsilon, then this is just the quantum dimension of alpha. Okay. So this turns out to be a kind of it's like this augmentation, like a trivial representation of a group algebra that we were dealing with there. All right. Well, if you know all this, it becomes pretty obvious what you would mean by a cohomology theory of such a thing.
This is not the same as the epsilon 2 lines above.
What?
There's an epsilon 2 lines above.
Oh dear, yes.
Pi is the definition of pi.
Yes. Well, I just yeah.
An alternative epsilon.
Let me call this epsilon E, and then yes. Thank you. I didn't notice that. Right. So, anyways, the way you can define now your homology, cohomology, whatever you want. For instance, let's go for cohomology of A. Well, it's really A, and then you well, let's just say A, but I mean A is not just taken as an algebra. It has all this structure of having this remarkable subalgebra B generated by all these projections pi, and also this augmentation. So, well, you fix a right A module, and if you want, you can think of it as an A bimodule by using the augmentation, making it into a left-right module, and then, well, your Cn is going to be Hom from, well, I'm just going to take the tensor power of A. The only thing is that what one should do is take care of this subalgebra B, and so what one does is this one takes a tensor product over B. So we do this n plus 1 times. And then, so let's call this module K. We'll look at it with coefficients in K. Now, because we will regard this K as a bimodule using the augmentation for the left action, and the augmentation anyways kills everything in my algebra except for things somehow degree 0, things which live under this projection, then actually I can put here this PE, the projection, onto the the trivial representation, and here also I can I mean, I somewhat hid under the carpet what really is a representation, but anyways, there's a certain sub-piece of that representation which corresponds to, I mean, I should really call it K0 or something like that. Okay? And right, and so these would be homomorphisms. Well, I can regard them as homomorphisms over A, or I can just get rid of this guy here and make it N like that. Yeah. And then you have D, same as before. Okay, and so this way you get a notion of cohomology. So, for example, again, the case n equals 1, so the situation of one cohomology, I'm just looking at maps that satisfy the usual kind of derivation relation, well, except that, as I said, we have this augmentation. Right. So these would be maps D from A into K. And then the inner ones, things of the form dx c of v, what is it, epsilon of dx c minus c acted upon by v, right? This is really the formula for what these things are. And so if you take all such derivations modulo the inner ones, you get what is called the first cohomology. Now, just as in the group case, there are some canonical choices of modules that you can take. So, choices for K, well, one choice is just to take epsilon. I mean, you have a, no, I'm sorry. One is to take A itself, and that leads into no, epsilon, right? So that leads into trivial coefficients. The other choice is to take L2 of A. Now, it turns out that there's a certain canonical trace on this algebra, which, let me not go into details of how to describe it, but it's more or less, in each piece here, which is just a kind of a matrix algebra, it's a certain multiple of the trace on that algebra. So here you get a kind of L2 cohomology, and you do retain the fact that the relevant cohomology groups remain modules over the von Neumann algebra generated by A. So you can compute these L2 Betti numbers of A as the dimension over this von Neumann algebra of A of HK. Now, there's a little wrinkle here, which is that this thing is a to infinity von Neumann algebra in general. I mean, it's not doesn't have a finite trace, but dimension theory equally well works there. Okay, now, as I told you equally well, the structure of this group-like nature of a subfactor. Now, I think I've backed myself into a corner here. There must be something with a hook that allows me to lower that board, because there's no way, unless I ask Stefan or somebody tall enough to lower this. Okay. Oh, I shouldn't have. I didn't mean to erase that. So the whole exercise was to point out that there is this alternative approach, not alternative truth, about subfactors, which is the symmetric enveloping algebra. And so the connection, I mean, in the most basic way, is that if you take this larger von Neumann algebra, so let's just call these T and S. So you have this inclusion of T and S. So that the whole point is that if you look at L2 of S and start decomposing it into TT bimodules, then what you recover are basically your objects in your category. So it turns out that here there's also a tube algebra. So like we had tube of C, there's also tube of T inside S. In fact, this tube of T inside S is more general than the kinds of things that you get from subfactors. It can be defined for any quasi-regular inclusion, and I'll point that out in a little bit why that's interesting. Its definition is kind of very similar. Let's write it A T inside S. This is the direct sum over I and J irreducible TT bimodules. So you decompose S into irreducible TT bimodules and you make choices for these things. And here you take again the Hom space between IS and Sj. You don't have to sum over alpha anymore because S includes all that, of course, in itself. There is a similar way to define multiplication and all the goodies. Now, the algebra that you get is Morita equivalent to the previous one. So that's kind of key. So these are same up to Morita equivalence. Well, one reason why this is kind of nice is because you can right away define a cohomology theory on this side, and it looks slightly different. So this time, what will happen to be Cn, it will be, you will end up taking tensor powers of, so involves tensor powers of S over T. Okay? And, well, one immediate corollary of the fact that these things are the same is that the cohomology of this T inside S is equal to the cohomology of the tube algebra AC. Now I put equal in quotation marks. Why? Because of course you have to put here coefficients, say V and V, but you have to translate what coefficients you have. I mean, a module over this T inside S is something that's equivalent to some other module over this algebra. You just have to make the translation. Of course, Morita equivalence precisely says that there's a correspondence between representations of these things. So I should say like V sub C or something like that. But this has a nice corollary, because if you take the case of trivial coefficients, so in this case the trivial coefficients correspond to choosing this V to be simply equal to T itself. What?
S probably. You want to S by module.
S, sorry. Right. So in that case, what happens is that when you actually compute HK of T inside S with coefficients in S, you get 0 if the index of S into T is 0. And this actually is a result of von Jones, who actually tried to use this kind of cohomology to create a cohomology theory for a subfactor directly. I mean, you just start with some factor n into m. sorry, not index, yeah. Finite index, I'm sorry, I did. So, right, so he tried to use this construction of cohomology to actually try to look at what happens when you do this kind of Hochschild type cohomology for T into S for a finite index inclusion, and it was kind of a disappointing result for him that actually you get 0 all the time. But in fact, it's not so surprising, because what this is saying is that if you now look at the cohomology of your tube algebra AC with trivial coefficients, that this is 0 if C is what's called finite depth. In other words, has a finite number of irreducible objects. And by analogy with groups, this is quite reasonable, because we saw that precisely for finite groups the cohomology always vanishes. So that's fine. Okay. Now I'm erasing this, but as I'm erasing this, you could start wondering what computations you can make with these things. And the answer is that, of course, very few computations can be done directly from this definition. There is the power of the reason that actually all this algebraic machinery was introduced in algebra to begin with is to enable you to use some homological algebra machinery to do this kind of algebraic topology computations that people have been doing in topology for ages before they were imported into algebra. And so, of course, the key idea is to replace or show that your cohomology, which is defined as the quotient of some zk modulo bk, actually is isomorphic to some z prime over b prime, where the z prime and b prime is derived not from the kind of very huge space like that, but a much smaller space, which is somehow geometrically motivated and is kind of ad hoc for a specific algebra, something called a resolution. So these are obtained using what's called a resolution. And being able to phrase this cohomology theory in this very algebraic way as some kind of Hochschild homology of this tube algebra A and so forth precisely allows you to do these kinds of computations. So let me just show you a couple of these. So for example, for L to Betti numbers, the kinds of things that we're able to show is that, again, if C is amenable, let me not go into that, but I mean certainly if you have a situation where you have these kind of Fellner sets, that definition of amenability, then the L to Betti numbers of your category vanish. You also have the same formula for free products. And similar, when k equals to 1, there's also some correction term as before involving the zeroth cohomology. This is the Kunith formula. Exactly as before. Okay? Oh, I should say maybe that the zeroth Betti number is 1 over the number of irreducibles in C. Right? So 1 over no, 1 over not the number of irreducibles, 1 over the depth. I don't know how you call it, the global index of, is there a notation for, all right, I'll just write it as S into T, where S and T are these symmetric enveloping things. Okay, now, it turns out that there is still a third picture for this cohomology, which is a graphical one. And since life is short, I will just very quickly tell you what it is for cohomology with trivial coefficients. So graphical picture for trivial coefficients. So this time around, you encode this standard invariant of a subfactor, this tensor category, and so forth, into a planar algebra. So this time you start with a planar algebra P. And of course, the engine behind is that there is a tube algebra of P, which has a geometric meaning. Namely, it's the space of all the annular diagrams like that with elements of P drawn in between. Okay, so elements of P which are drawn inside an annulus and the strings of those diagrams connected any way you want. Right, so for instance, if P is the Temperley-Lieb-Jones planar algebra, this just means that you have some annular non-crossing partitions sitting inside, drawn inside this annulus. So it's an algebra under composition. You can glue such things in and out, and then you have to worry about the number of strings, and that kind of corresponds to the fact that there are these PIs that are and the multiplication is 0. They don't match. Anyways, if you look at your complex CK, so this is, again, I'll take trivial coefficients. Well, it turns out that what you have to do is you have to take a sphere with some number of punctures, n punctures, and then you can draw your elements of your planar algebra any way you want in that sphere with some number of points removed. So you just do something like that. Whatever. Complicated drawing like that. And the differential of the complex is -1 to the k, remove point number k. So you remove these points one by one, and that causes some strings to contract, and that gives you, so this I guess is actually a homology complex, because the number of strings goes down. So so then you look at the kernel of the module of the image of D. And it has been an interesting mystery what's going on there. Now, of course, again, your hero of the day is Merita equivalence. That tube algebra of the of this planar algebra is again Merita equivalent to this tube algebra. So its cohomology can actually be computed if you were to compute the cohomology of the tube algebra. And well, it was a little mystery. What is the homology of Temperley-Lieb-Jones with trivial coefficients? And in our paper with Sorin and andStefaan, we were able to prove that this is 0 if k equals to 0, 1, or 2.
No, it's C when it's 0.
Oh, sorry, C, yeah, you're right. C if k equals 0. And now there's a paper that just came out as of yesterday, I guess, right, by Kied, Raum, Stefan Vaes, and a student of Stefan. Michael, right? Anyway, so they were able to actually show that this is C again if k is equal to 3, and then 0 if k is bigger, is strictly bigger than 3. And I mean, this is actually kind of funny, because if you go back to this situation with the sphere, I mean, this just really, this complex consists of all possible ways of drawing these kinds of circles in nested ways on the sphere. And the complex is the obvious one. I forgot to say, this is, of course, where delta is in the generic case, so delta is bigger or equal than 2. If delta is less than 2, then it's 0. Well, at least all of these are 0. The 0th one is special, but all of the other ones are 0 by our theorem, because it is finite depth, so everything vanishes. So they are able to compute this, and at the heart is a resolution of length 3. So in fact, they establish a much deeper fact that the Temperley-Lieb-Jones tube algebra has homological depth 3. So that's very nice. And in that same paper, they have many computations of L to Betti numbers of categories coming from quantum groups. In fact, they show that this is the same thing as what was called the L to Betti number of a quantum group before. And so that gives quite a number of definitions. Now, I want to finish with just 2 comments. One, there was always a competitor to this definition early on, which is that, of course, you can, whenever you have the C star tensor category and so forth, you simply have something called a fusion ring. And it was always very tempting to say, well, let's just take the fusion ring. Now, everybody who wanted to do this was always aware of the fact that you're throwing away the baby with the bathwater. I mean, you're ignoring most of the structure, but, you know, that was a viable thing to do. And actually, Stefan is telling me that this gives you an example of something where the fusion ring does not give the correct answer. So, examples where the Betti numbers of the fusion ring are not that. So they're not the L to Betti number of the quantum group, and I mean, as it should be. So that really is yet another evidence of the fact that this is really the correct definition. The other thing that I wanted to emphasize by way of explaining why it's interesting to look at this quasi-regular inclusion in the more general case. I mean, rather than starting with a subfactor situation, you can look at the situation where T is abelian, and then S is, well, in general, the von Neumann algebra of an equivalence relation, or a cross product, for instance, L infinity of X by gamma, or more generally, L of an equivalence relation R. And when you do that, if you properly process our definition and so forth, you recover Damien Gaboriau's work for cohomology of the associated measured groupoids, in particular the theory of L to Betti numbers. So recover Gaboriau L to Betti numbers. So somehow the subfactors are like a common situation where all of these definitions give you the same thing, and as you saw, the viewing it from a slightly different angle sometimes gives you non-trivial results. But individually, these results can be kind of pushed beyond the subfactor situation, and this being one example of it, where you can take a an inclusion like that does not come from initial inclusion of subfactors, and still, of course, gives you a beautiful theory to do with that. I think that's all I wanted to say, so thank you very much.
If you have grading into the C star tensor category, do you get more information?
Well, I mean, somehow the first thing that I mean, the short answer is that I don't know, except that somehow when you go to this tube algebra, one passes to this quantum double, which always is braided. So somehow I'm not sure that the initial existence of braiding is very visible, but actually I don't know. I don't know.
This is not a question, it's a comment. There's another place where one has the same cohomological phenomenon where everything is 0 except in dimension 3, and that's for the Virasoro algebra. So I just know that Virasoro algebra tends to be related to Temperley-Lieb, and I wonder if this non-trivial H3, which is the unique non-trivial thing in both cases, have something to do with each other.
Yeah, I don't know. I mean, I think in truth, I mean, I haven't had a chance to absorb this paper in detail, but in truth, I mean, it does prove this result, but I don't think there's an explicit cocycle you can write down that generates the cohomology. At least that's has not been done yet, as far as I know. I mean, explicit cocycle in the original picture, right?
You can write an explicit one if you want.
Okay. But it would be interesting to see what that is. I mean, what is the
Because
explicit?
in the meanwhile, and that's then the more conceptual explanation. So Yuki Arano wrote to me that he actually can go much further. So if you take a Q deformation of a compact simple Lie group, what he can show is actually that with trivial coefficients, and then for the representation category of this Q deformation, what you really get is C in the dimension of that Lie group in general. So it's really like a homology for this real form. And in this case, it's really because SL2Q is three-dimensional.
Right. So, but I don't know if it's connected with Virasoro. So. No, you wanted to.
I was gonna ask the question you just answered.
Okay.
Not just that it's a three-sphere. I mean, SU2 is a three-sphere.
Yes.
So this is cohomological three-sphere.
Right.
Yes. No. This is because of this representation category thing. It's really more of a quantum double thing, and therefore it would be SLQ2C rather than SU2 as a compact group.
It's a spherical thing with it's always one copy of C in some dimension.
Yes.
Other questions or comments? Or if not, let's thank the